Well, hello and welcome again to our journey into complex analysis. Very short section here just on complex series, just to introduce these before we start looking at Taylor and Laurent series. So I'm going to cover this in some haste, since much of the theory of summation of sequences of real numbers carries easily over to sequences of complex numbers with little change. The absolute value, of course, just gets replaced by modulus. So just a review of the basic facts. We have a set A of real numbers is said to be bounded above if there's a real number m such that A is less or equal to m for all A in the set A. If the set of real numbers is bounded above, then there's a unique number which is an upper bound for A and less than or equal to every other upper bound for A. If there is such a thing, then that's called the least upper bound or supremum for the set A, denoted by sup of A. If a set A is not bounded above, then we'll write sup A equals infinity. These definitions only apply to real numbers, since we don't have a notion of less or equal to in the complex numbers. But we will nonetheless need these ideas when we start looking at the modulus of complex numbers, which will then get us back into the real world. So a sequence of real numbers looking like this is said to be summable if the limit of the partial sums exists as n goes to infinity, and this is the same as saying this infinite series converges. A sequence of complex numbers is said to be absolutely summable if the absolute value is summable. And of course you can either think of this as absolute value or modulus. If you want to think of these as a complex series, then this will be the modulus of the ANs. We will only be concerned with absolutely summable series, and so just use the word summable to mean absolutely summable. Now, since this basic inequality, the modulus of the absolute value of the real part of z is less or equal to the modulus of z, and similarly for the imaginary part for all complex numbers, it follows immediately that this complex sequence is summable. If it's summable, then the real and imaginary parts are also summable. And of course the sum and scalar multiple of summable sequences are summable. Now we're going to be looking at series of complex numbers, but complex functions. That's going to be what our main point of interest from now on. So suppose now you've got a sequence of complex functions, f sub n of z, n equals 1 to infinity, defined on a domain D. We say that the sequence converges to f of z on D means that for each fixed z in D, then the limit as n goes to infinity approaches this function f of z. So in terms of epsilons and n's, this means that given epsilon bigger than 0, there is an integer n, so that if we go past there, that will imply the difference between this nth function in the sequence minus its limit function is less than epsilon, and this n depends on epsilon only and not on z. Sorry, I should say it depends on, at the moment, it depends on both epsilon and on z in general. But if the n does not depend on z, then we say that the sequence converges uniformly. That's an important idea you will have met in real analysis courses. So given an infinite series, sigma of a sub k of z of functions, we say that the series converges to a of z if the sequence of partial sums, this one, here's our sequence of partial sums, if that converges to a z. In this case then, this limit is the same as the difference in these two limits, which is 0. So that means for every z the general term must go to 0 as n goes to infinity. This should be all, I hope, revision from terminology from earlier courses, and we say that the series converges uniformly on D if the sequence of partial sums does. Uniform convergence, of course, is very, very useful, as the following result shows. It says that we can interchange limits and integrals. So if f sub n of z is continuous for each n, and we suppose that this converges uniformly to some function f of z in the domain, then f of z, the limit is continuous, and for any path in D, the limit of the integral of this sequence is equal to the integral of the limit of the sequence, and the limit of the sequence, of course, is f. And you will have seen this idea in courses in real analysis, and the theorems carry across nicely into complex analysis. You probably will have also come across this very useful tool in analysis called the Viastras M Test. So if we have a sub m of z as a sequence of complex functions, so that each of these terms is bounded by m sub n, depending only on n and not z, for all z in D, and if the sum of these m's converges, then the series of these functions converges uniformly in D. This is a very useful, very powerful tool. The proofs of these last two have been done in standard courses of analysis, and the proofs carry across nicely into complex functions. As an application of Viastras M Test, we have a corresponding ratio test, as we do corresponding to the one you have in the real world. That is, if A1 of Z is bounded on D, and if the quotient of successive terms is less than or equal to m, and m is strictly less than 1, then this sequence, this infinite series, converges uniformly. And I'll put a little proof of that here because it's fairly easy. So we can write our a sub n as a1 over a1, a2, and so on up to there. So you think of all these cancelling out. Now, since a1 of z is less than a in modulus for some a, then that means the modulus of this is less than a times, now each one of these is bounded by some m. And so I'm going to get a times m to the n minus 1 here, an m for each of these terms in here. Now a times that, this is a geometric series, so I can multiply that and I get this, and this converges to this because m is less than 1, so I've got a nice simple geometric series. And then by the Viastras M test, we've now shown that the modulus of this is bounded for each n, and so Viastras M test gives the result. Just a little exercise just to play with here, using the ratio test to show the following series converge uniformly in the given regions. So to show that this series here, sigma z to the n is 1 to infinity, converges inside a disk whose radius has to be strictly less than 1. And this one here is another nice series, show that this converges uniformly, where in a given region R, where R is less than the real part of Z and R is positive. So a couple of little challenge problems there, little exercises to work through to practice these ideas. And then in the next section we're going to start looking at Taylor series and Laurent series.